So today let's start with the Heaviside unit step function. Heaviside unit step function. This function is defined as capital U t minus a. This is equal to 0 if t is less than a, and this is equal to 1 if t is greater than a. So the graph would be something like this. This is t along the x-axis, and along the y-axis we have u of t minus a. A is some point on the x-axis, and here we have 1 unit on the y-axis. So the function is 0 for all values of t less than a. So for all values of t less than a, the function is 0. And then at t equal to a, it suddenly jumps to the value 1, and then continue 1. So at t equal to a, it suddenly jumps, and then its value continues to be 1 thereafter. So this is the Heaviside unit step function. Okay. And what is the use of this function? It is possible to express various discontinuous functions in terms of this unit step function. So let me write it down here. It is possible to express various discontinuous functions in terms of the unit step function. In terms of the unit step function. Okay. Then let us find out the Laplace transform of this unit step function. So example, last time we discussed 2 examples. So this is example 3. Laplace transform of the unit step function ut. Let us take a equal to 0 here. Okay. As the first example, let us take the Laplace transform of ut. So this is equal to integration from 0 to infinity ut dt. And what is ut? Ut is ut is equal to 0 when t is less than a. And what is a here? Here in this particular example, a is 0. So for values of t less than 0, it is 0, and for values of t greater than 0, it is 1. So the limits are from 0 to infinity. Sorry, I forgot to mention the e to the power minus st term here. Sorry, here we should have e to the power minus st then dt. Okay, so here it should be 1 times e to the power minus st. That is simply e to the power minus st dt. And what is this? This is integration minus e to the power minus st divided by s in the limit 0 to infinity. Okay, and last time we saw that when s is greater than 0, the value of this e to the power minus st at t equal to infinity is 0. Okay. When t tends to infinity, if s is positive, then this term e to the power minus st becomes 0. So what remains is only e to the power minus st calculated at the limit 0, t equal to 0. So this is simply 1 by s, where s is greater than 0. Thus, the Laplace transform of ut is 1 by s. That means the inverse Laplace transform of, therefore, the inverse Laplace transform of 1 by s is ut. Okay. This unit step function may also be obtained from the function. Okay, the unit step function, may also be obtained from the function ft. This is equal to 0 if t is less than 0, and this is equal to e to the power k times t. K times t when t is greater than 0 by taking the limit by letting k tends to 0. Okay. So when k tends to 0, this becomes 1. Okay. So unit step function can also be obtained from this function by letting k tends to 0. And when we take the Laplace transform of this function, we get the Laplace transform would be 1 by s minus k. And in the limit k tends to 0, the Laplace transform becomes 1 by s, similar to the result which we have obtained just a few moments earlier. Okay, so this is the Laplace transform of the unit step function. Okay, then let us consider another example. There is example 4. Let us find out the Laplace transform of u of t minus a. Now let us find out the Laplace transform of u of t minus a. Earlier we found out the Laplace transform of ut and we found that it is 1 by s. Now let us find the Laplace transform of the unit step function calculated at t minus a. This is equal to integration from 0 to infinity. This is equal to integration from 0 to infinity e to the power minus st u of t minus a dt. And what is u of t minus a? U of t minus a, we just saw that u of t minus a is, this is equal to 0 when t is less than a, and this is equal to 1 when t is greater than a. So, so this is 0 when t is less than a, and this is equal to 1 when t is greater than a. That means we change the limit to a to infinity e to the power minus st multiplied by 1. 1 multiplied by 1, we don't need to write it explicitly, so we simply write dt. Okay, and this is minus e to the power minus st by s, and the limits are from a to infinity. And when s is greater than 0, we have seen earlier that the value of this function at limit t tends to infinity is 0. So what remains is only e to the power minus sa divided by s. So the answer is e to the power minus as divided by s, where s is greater than 0. Okay, this is fine. So this is the value of the Laplace transform of the unit step function. That means the inverse Laplace transform. Okay, so that means the inverse Laplace transform of e to the power minus as divided by s. This is nothing but u of t minus a. Okay, this is fine. Now let us look at another example, which is an application of the linear property. Example. So let us remember the linearity property. Linearity property. Linearity property of the Laplace transform. What did it say? It says that the Laplace transform of C1 F1t plus C2 F2t, where C1 and C2 are some constants, F1 and F2 are arbitrary functions of t, and this is equal to C1 times the Laplace transform of F1t plus C2 times the Laplace transform of F2t. This was the linearity property which we discussed earlier. Okay, now let us see an application of this property. So example number 5. Let us find out the Laplace transform of e to the power, say e to the power I omega t, I omega t. Okay. Last time we saw that the Laplace transform of e to the power at, the Laplace transform of, let me write it somewhere here in the right hand side. Last time we saw that the Laplace transform of e to the power at is equal to 1 by s minus a. This we saw in our last class. So here, what is the value of a here? The value of a here is now I omega. Okay, I omega. That means the Laplace transform of e to the power I omega t is 1 by s minus I omega. Okay, now this is a complex number in the denominator. So we multiply both the denominator and the numerator by its complex conjugate. So what do I get? I get s minus I omega multiplied by s plus I omega. And in the numerator, I have s plus I omega. Okay, so what do we get now? We get s minus I omega, s plus I omega. This would be the square of the modulus of the complex number. So this is s square plus omega square. This is s divided by s square plus omega square plus I times omega divided by s square plus omega square. Okay, we can call this equation number 1. Now again, let us calculate the Laplace transform by using the Euler's formula, e to the power I omega t. And we know that e to the power I omega t by Euler's formula, this is e to the power I omega t is cos omega t plus I sin omega t. So this is cos omega t plus I times sin omega t. Okay, e to the power I omega t is cos omega t plus I times sin omega t. This is the Euler's formula. Now let us apply the linearity property here. So Laplace transform of cos omega t plus I sin omega t, if I apply the linearity property here, what do I get? This is the Laplace transform of cos omega t plus I is a constant. I take it outside. Laplace transform of sin omega t. Let us call this equation number 2. Now let us compare equation 1 and 2. So comparing equations 1 and 2. What do we get? This is equation 1. This is equation 2. The left hand sides of equation 1 and 2, they are the same. That is the Laplace transform of e to the power I omega t, Laplace transform of e to the power I omega t. So the left hand sides of equations 1 and 2, they are the same. So the right hand sides should also be the same. That means this expression should be equal to this expression. So this is a complex number and this is another complex number. And when are two complex numbers said to be equal? Two complex numbers are said to be equal if their corresponding real parts are equal and their corresponding imaginary parts are equal. That means this real part should be equal to this real part, and this imaginary part should be equal to this imaginary part. So from this we get that Laplace transform of cos omega t is s by s square plus omega square, and the Laplace transform of sine omega t is omega by s square plus omega square. We get the Laplace transform of cos omega t. This is equal to s by s square plus omega square, and the Laplace transform of sine omega t. This is, from these two expressions we get omega by s square plus omega square. Okay, so we have calculated the Laplace transforms of cos omega t and sine omega t by using the linearity property of Laplace transforms. Okay, let us look at another example. Okay. So what was the last example? The last example was example number 5. So now this example is example number 6. Let us find the Laplace transform of t to the power a. T to the power a, where a is some constant. Okay, then this is equal to integration from 0 to infinity e to the power minus st t to the power a dt. Okay, so this is from 0 to infinity e to the power minus st t to the power a dt. To solve this, we convert this to a gamma function. So to convert this to a gamma function, what do? We substitute st equal to some variable x. So let us substitute, put st equal to x, where x is some variable. Then that means t equal to x by s, and dt is equal to dx divided by s. Therefore, this integral becomes, so the Laplace transform of t to the power a, it becomes integration e to the power minus st. So st is x, so this is e to the power minus x, and t to the power a, t is x by s, x by s. So this is x by s. Sorry, this is not a, this is x by s to the power a. And what is dt? dt is dx by s, dx by s. And what are the limits? When t is equal to 0, when t is equal to 0, x will also be 0. When t is equal to infinity, here x will also be infinity. Okay. So here the integration is with respect to the variable x. So the s, this s is a constant, and I can take it outside. So this is, we have 1 by s to the power a multiplied by 1 by s. So this is 1 by s to the power a plus 1. Integration 0 to infinity e to the power minus x, x to the power a dx. And we see that this is a gamma function. Okay, and this is equal to 1 by s minus a. So 1 by, sorry, s to the power a plus 1. This is not s minus a, this is s to the power a plus 1. And this is gamma function. This is gamma a plus 1. So gamma a plus 1. Okay, so this means a should be greater than minus 1, because gamma 0 is not defined. Okay, so this is the Laplace transform of the function t to the power a. Okay, that is fine. Now let us look at another example. Example 7. Consider the rectangular function. Consider the rectangular function w t minus a comma beta defined by w t minus a comma b. This is equal to 0, where t is less than or equal to a, and this is equal to 1 when t lies between a and b, and this is equal to 0 when t is greater than b. Okay, and what is the plot of this function? The plot of this function would be something like this. This is t, this is w t minus a comma b, this is w, this is a, this is b, this is a, sorry, this is a, this is b. So for all values of t less than a, it is 0. So this is 0. Then the moment t is equal to a, it jumps to the value 1. And then from t equal to a to t equal to b, it remains 1. And from t equal to b, it continues as 0. Okay. So this is the graph of the function. Let us find out the Laplace transform of this function. Okay. So the Laplace transform of w t minus a comma b. This should be equal to integration from 0 to infinity e to the power minus st w t minus a comma b dt. And this is equal to, for all values of t less than a, the function is 0. And for all values of t greater than b, the function is 0. So the function is non-zero only during the interval a to b. So the integration would be from a to b, e to the power minus st, e to the power minus st. Then the value of the function in the integral a to b. The value of the function in the range a to b is 1. So that means we multiply this by 1, and we don't need to write it explicitly. So dt. And this is nothing but e to the power minus st divided by minus s from a to b. Okay. And this is equal to 1 by s integration e to the power minus as minus e to the power minus bs, where s is greater than 0. Okay, s is greater than 0. This condition is really not required in this particular case. Okay. So this is the Laplace transform of the function wab. Okay. Now let us write this function in terms of the Heaviside unit step function. Okay, I repeat, we can express this function w t minus ab in terms of the Heaviside unit step function. Okay. Here, let me write it here. We can also write w t minus a comma b is w t minus a comma b. This is equal to u of t minus a minus u of t minus b. Okay. And then if I take the Laplace transform of this, then Laplace transform of w t minus a comma b, this is equal to Laplace transform of t minus a, u of t minus a minus Laplace transform of u of t minus b, where I have used the linearity property here. And this right hand side, this is equal to 1 by s e to the power minus as. This is minus 1 by s e to the power minus bs. And this is equal to 1 by s e to the power minus as minus e to the power minus bs. This is the same result which we obtained just a few moments earlier. Okay. Okay, so this is fine. Okay. Now, using this expression, using this function w, let us try to find out the Laplace transform of Dirac Delta function. And let me mention a few things about the Dirac Delta function first. So let me first write about Dirac Delta function. Very often, we may have a large force or a large voltage in a system acting for a very short time. Such an impulse is usually idealized in terms of the Dirac Delta function. And the Dirac Delta function is following through this Dirac Delta function is defined through the following equation. The Dirac Delta function, delta x minus a, this is defined through the following expression. This is equal to 0 for x values of x not equal to a, and this is equal to infinity for the value x equal to a. Okay, so I have a very thin spike, infinitely tall spike at the point x equal to a, and this is represented graphically as, this is represented like this. This is the x-axis, this is the delta function. This is at x equal to a, this is the origin. Okay, so the Dirac delta function is defined through the following equation and this integral. A minus alpha, a plus beta, delta x minus a dx. This is equal to 1, where alpha is positive and beta is also positive. Okay, these two equations, they define the Dirac delta function. Okay, and this Dirac delta function is an infinitely thin spike having a unit area. Okay, and this spike is at x equal to a, and it is usually represented by an arrow of unit height. Okay, it is normally represented by an arrow of unit height for an arbitrary well-behaved function f of x. So let me write one more property here. For an arbitrary well-behaved function f of x, which is continuous, at x equal to a, we have integration from a minus alpha to a plus beta. So alpha and beta are positive numbers. F of x delta x minus a dx, this is equal to f of a. Okay, so the Dirac delta function has this property that integration from a minus alpha to a plus beta, f of x delta x minus a dx is equal to the value of the function calculated at the point x equal to a. And this limit, it can also be written as from minus infinity to plus infinity. Even if you take the limit from minus infinity to plus infinity, the result will remain unchanged. So when I replace this to upper limit and lower limit by plus infinity and minus infinity, this result will remain unchanged. Okay, so this is the Dirac delta function. And strictly speaking, the Dirac delta function is not an ordinary function, but it is a distribution. In the strict sense of the term function, Dirac delta function does not qualify as a function. Strictly, it is a distribution, but we still refer to it as the Dirac delta function. Okay. So let us try to find out the Laplace transform of Dirac delta function. Let me write it on a new sheet of paper. Okay, this is fine. Example. What was the last example that we discussed? The last example was example number 7. This is example number 8. Okay. Here, one approximation. One approximation to the Dirac delta function is constructed as one approximation to the Dirac delta function is constructed as delta t is equal to limit 1 by epsilon w t comma epsilon in the limit epsilon tends to 0. Okay. So let us try to calculate the Laplace transform of Dirac delta function by using this property. So first let us calculate the Laplace transform of this 1 by epsilon w t minus epsilon. So Laplace transform of 1 by epsilon w t comma epsilon. This is here, this Laplace transform we are going to integrate with respect to t from from 0 to infinity. So in this particular case, epsilon is a constant. So I can take epsilon outside. So this is epsilon 1 by epsilon Laplace transform of w t comma epsilon. And we already know that the Laplace transform of w t minus a comma b is 1 by s e to the power minus as minus e to the power minus bs. So this is equal to 1 by epsilon 1 by s e to the power minus as. So t minus a, here a is 0. So this is e to the power minus 0. Minus 0 is the same as 0. So we don't need to put the minus here. Minus e to the power minus bs. And here b is epsilon. So e to the power minus epsilon s. Okay. This simplifies to 1 by epsilon times s 1 minus e to the power minus epsilon s. Okay. Now let us expand e to the power minus epsilon s in a Taylor series about the origin. Okay. So this is 1 by epsilon s 1 minus this, the expansion of e to the power minus epsilon is 1 minus epsilon s plus epsilon s whole square by 2 factorial minus epsilon s whole cube by 3 factorial and so on. This one and this one, they cancel out. What remains is 1 by epsilon s minus epsilon s whole square by 2 factorial minus epsilon s whole cube by 3 factorial and so on. Now, if I divide by epsilon s throughout, what should I get? I should get 1 minus epsilon s by 2 factorial. Sorry, this is minus, this is plus. Okay, so this will be minus. So 1 minus epsilon s by 2 factorial plus epsilon s square by 3 factorial. Oh, 1 epsilon s here cancels with 1 epsilon s here. So we are left with only epsilon s square and so on. Now to find delta, we take the limit epsilon tends to 0.